Okay, when we create scatter plots, many times we will see that there may be a line that kind of goes through that. That line we call a regression line. It shows a relationship between whatever the two quantitative variables that are the response and explanatory variables, and hopefully they try to show a relationship there. We use this regression line to make predictions for values of x that was not included in our data set. We try to predict what those y values would be. Okay, so here's an example. Here to the right here, we have a scatter plot of non-exercise activity measured in calories and measured fat gain measured in kilograms after 8 weeks for 16 healthy young adults. And we can see here that the scatter plot here there is a relationship there. It is relatively linear. It is a negative relationship, and it's moderately strong, okay? And that line that goes to the middle there is called a regression line. And the regression line shows that as your non-exercise activity increases, your fat gain decreases. Okay, a regression line is a model for the data. Again, we use it to make predictions for whatever the two quantitative data things that we are looking at. The regression line always has the form of y hat equals a plus bx. And this is a new symbol that you need to become familiar with. Y hat has a y with a little up caret above it, and we read that as y hat. It is the predicted value, okay, where y is always the actual value. We use y hat to represent the predicted value, which is the equational line, because the line is a prediction. And it's in the form of a plus bx. A being the y-intercept, and b being the slope. I know in algebra you learned that as mx plus b, and b was the y-intercept. In statistics we use the letters a and b, where a again is the y-intercept, and b is the slope. So again, make sure you record this in your notes. Okay, a couple things I want to emphasize with the slope. The slope is the amount by which the y is predicted to change when x increases by 1. You remember, slope is always the change in y over the change in x. And so we can always take the slope, that number in front of x, and rewrite it over 1. And if we do that, we think of the slope itself as being the change in y, and the 1 as being the change in x. And we always have to interpret this within context and statistics. And once again, it would be the amount that the b changes every time x changes by 1 unit. Where a is the y-intercept, this is the value of y when x equals 0. And we also call this the starting point. Many times our equation doesn't really make sense with a starting point. Sometimes it does, but many times it does not. But we always have to interpret it and then to make a determination about whether it would make sense for the given situation or not. So we look at this example of the relationship between non-exercise activity and fat level, or fat gain. We can see here that this equation here, which goes through the middle of these lines, remember this is a negative linear, moderately strong regression line that goes through the middle of these points. We use this line to predict different values of x that may or may not have shown up in our data set. And we need to always be able to identify the slope and the y-intercept of that. So in this case, let's assume that this is the equation of our regression line. 3.505 minus 0.00344 times the amount of non-exercise activity change. So remember, b is the slope, that number in front of x, which this is our variable. Okay. And the y-intercept then is 3.505. So if we were to interpret this in context, we would say that this is the amount of fat gained is predicted to go down by 0.0034 kilograms for each added calorie of non-exercise activity. And because of the negative, that's why we're predicting it to go down. The y-intercept, which is the 3.505, is the fat gain estimated by this model if our non-exercise activity does not change when a person overeats. And in this case, I think the y-intercept actually seems to make sense. If I don't exercise, then I'm going to gain weight, gain fat. So that does make sense. Not always does it make sense, but in this situation it does. So it's, again, you need to practice at being able to interpret both the slope and the y-intercept within context. In other words, put it back into the scenario that was given to you. Well, like I mentioned before, regression lines are used to make predictions, and predictions, hence why we have the symbol y hat for our regression line, because it is a prediction. But we can actually use it to predict very specific values of our x-axis. So for example, if we were to try to predict how much fat gain a person would have who's non-exercise activity increases by 400 calories, we could actually plug 400 into our equation and get an answer here. And so this is what I did. I took 400 and plugged it into our equation, and the amount of fat gain we got was 2.13. And this is going to be what we call an interpolation. Very important to understand that when you use it to predict for values that comes within our data set, these tend to be very, very accurate. So if you notice, we collected data everywhere from negative 200 up until about 700 or so. And so because our prediction, if you notice, came within that range, this will be very, very accurate. And as soon as we try to predict outside that range, so for example, if I tried to predict what happened at 1,000 or something bigger than that, then many times our prediction is not going to be as accurate because we don't have any data out there that will help us see if this continues to be aligned as our non-exercise activity increases. So once again, interpolation is when you predict within your data set. Extrapolation is when you predict outside your data set. Interpolation, very accurate. Extrapolation can be inaccurate at times. So again, extrapolation is a situation where you predict outside of your given data sets, and that will show many, many times will make our prediction will be not accurate. So again, a definition you need to write down is extrapolation is when we use a regression line to predict far outside the interval values that we collected, and they usually many times break down, and our predictions aren't very accurate for extrapolations.